Yeah, thank you for the introduction. And yeah, thank you all for being here at this late time of Friday. And well, yes, my presentation is on learning Lagrangian fluid mechanics with equivariant GNNs. And so yes, my talk will be much more applied than most of the other talks. So there will be rather less equations and deep learning. So yeah, let's start. So first, yes, I also want to mention my collaborators because this work wouldn't have happened without them. And so Gianluca is one of my students who is sitting here. Exactly, the person in the middle is my supervisor, and Johannes was helping us along the way. So my talk will be split into 4 parts. So first I want to introduce the data. So well, as I said, deep learning and so data-driven sciences. And so the question is what problem are we looking at, right? So the second section is on how people solve this type of problems classically, right? And so they are trying to argue why that's not the best thing to do, like why I am here. The third thing is our methodological contribution, and the last section are the experiments. Okay, so the data sets. Fluid mechanics. So there were a few talks mentioning fluid mechanics, right? There was the Millennium problem and all these things. So here we are purely on the applied side, right? So we want to solve these problems in like numerically discretized to know the solution on a given domain. And so this is one of these typical problems among fluid people, like engineering fluid mechanics. And so this is a decaying problem. So we're talking about the viscous Navier-Stokes equations, and this is the decaying 3D Taylor-Green vortex, which is a very interesting problem from the perspective of people studying turbulence. So you might have heard of turbulence. This is a mode of the dynamics of Navier-Stokes. And so this problem was designed as a toy example to an extreme case of turbulence where we move from an initial laminar structure to turbulent, and so there's the transition and all these things. So this is one of the data sets we have, and this is another one which is also kind of typically seen in literature, being so it's something like a channel flow, but like 2 of them to have all periodic boundary conditions and to not care about boundaries because we don't want to go there for now. And so we're looking at physical properties among other properties. And so one of these properties is the kinetic energy. And by kinetic energy, I mean the squares of the velocities of all of these particles which we use to discretize space. So how have people been tackling these problems? Well, it all started in the 1970s with people in astrophysics trying to simulate galaxies, and so they started developing these particle-based methods. And by particle-based methods, I mean so there is some domain over which we want to know the solution for some initial state and some Navier-Stokes dynamics in this case, but some equation and initial state we want to know the temporal evolution. And there are 3 ways essentially to solve this problem. One is to discretize the space with regular voxels and grids, or a mesh, or particles. And so I'm looking at the particles, and my particles are moving, meaning we're talking about the Lagrangian description of like Lagrangian framework. So what happens here? Well, there's this kernel interpolation, and this is essentially the smoothed particle hydrodynamics thing. Like this is this kernel interpolation, and so essentially SPH, this method, takes Navier-Stokes and represents Navier-Stokes in terms of kernel interpolations of the terms of Navier-Stokes, right? So we get something that comes from Navier-Stokes, but is then discretized on the bottom of Navier-Stokes. So we're talking about incompressible Navier-Stokes, right? And yeah, so we just discretize Navier-Stokes and we get a system of ODEs, and so this is something we can solve. Okay, cool. This is what such an algorithm looks like. And essentially what we are trying to do is to replace the core of this thing. So because we work with particles, we need to define somehow interactions, right? And so we define them based on a radial distance, being like Euclidean distance. And this thing we cannot replace, and so machine learning should not know how to do this, but it should know how to compute interactions out of this graph. And then there are all these terms that, as I said, come from Navier-Stokes. These like three accelerations: A, pressure, viscosity, and force. And so yeah, this is pretty much all of it. And we keep the numerical integrator being well. There's a whole variety of them, but so we work with symplectic Euler, which is well one of the simplest ones essentially. Yes. So that's what people have been doing, like except for the learning. But so why the learning? And so yeah, I wanted to ask you. So why do you think that we want to learn Navier-Stokes? Like why is it useful? Anyone? Like I mean, people have been developing these methods for like more than 50 years almost. So yeah, why are these methods not enough? Like what is it that they cannot do? Thanks. Okay, so yeah, it is turbulence. It is turbulence, and the problem with turbulence is if you want to solve Navier-Stokes to like a level of accuracy that we eventually want, to get the correct solution for the Navier-Stokes equations, eventually for like high Reynolds numbers, meaning very, very dynamic flows in some sense, we would need to have very very small cells or particles, meaning the resolution would need to be very high. Meaning if you want to simulate very wild flows, then we eventually need way too many cells. Like even for simple problems, we need like eventually millions of like particles, like discretization points. And so, well, that's prohibitive well, from some level onwards, right? And now the thing is, if we don't have this high resolution of the discretization, we don't get the solution to Navier-Stokes, we get the solution to something else. And this something else is not Navier-Stokes, and it doesn't even look on the large scale like Navier-Stokes. And well, that's why I think machine learning. Now I put this slide just to it's a completely made up hierarchy, by the way. Don't try to Google this; you will not find it. It's rather the roadmap of my PhD to some extent. So that's where we are now, and what we submitted to GSI, and eventually I'll try to go all these levels out of the center. But so laminar flows are these simple flows which are not turbulent, and so they're not particularly relevant. But if we can handle them and like learn them to some extent, then that's already good news. And so a temporal coarse graining is the thing where so numerical simulators require some integration time step, right? And so in this particular work, we do 10 times larger time steps, and 10 times larger means something like well, so much that we lift the linear regime on. So if we have very small steps, we eventually do like yeah, well, linearize the dynamics, and so here we're not this linear. So to our method and to how machine learning people approach these problems, well, we have a series of frames, like snapshots of the system, right? And so we can take the last few of them, and so we want to predict the next one. And what we do is we compute the acceleration, which is the difference of velocities, and so we not classically integrate, right? But so that's the problem setup, and this is okay. This did not look like it before, but so yeah, eventually, so this curve is the perfect trajectory. But so because we learn effective dynamics, we want to learn these straight lines, which are well more nonlinear, right? And this is what people have been doing before us. So this paper is from 2020, and this is pretty much where I started when I started. So this is a classic message passing neural network. So I guess some of you know about neural networks, and so we start on the left. So there are some particles. These guys have solved pretty much the same the systems of the same type and of complexity. And so we start with particles, construct a connectivity graph based on a radius, like this thing over there. So for each particle, find the neighbors. Then we do so x are the physical properties being past velocities or whatever past information we have. Then we encode this thing with the graph neural network to a latent space, and then we have a bunch of layers on this latent space. So let's say this is 5-dimensional or something. or 15. So you have 5 past velocities in 3D. It's like 15 numbers, and then eventually this space here is like 100 dimensional, 128. So we have a bunch of these layers, and then we decode from the latent space to accelerations. And so that's here, and then we integrate. So that's this thing that was there before us. And now, well, the last 2 years have been very active in geometric deep learning, for those who have heard of geometric deep learning. And so, I mean, we had the geometry conference here. So that's what has been happening in molecular machine learning. Like, learned interatomic potentials is where this whole thing started, kind of like 5 years ago, or well, definitely not more than 5 years ago. So people have been trying to use spherical harmonics embeddings of vectors to achieve equivariance and then learn better interactions. So the idea of equivariance is essentially that if you have two, like the water molecule, and so there are some displacements and some interactions between the atoms. Now, if we give these like positions in the Euclidean space to an MLP, and then we get some accelerations. But if we rotate this somehow, and then we give it to the same MLP, the output is not rotated the same way, right? And so we can achieve this perfect mapping, like equivariant mapping between inputs and outputs with, well, equivariance. And so well, one of the methods that came out last year, or like on arXiv 1.5 years ago, is the stereo-equivariant graph neural network by Johannes Brandstätter, Max Welling, and so on. And so this is the general framework which allows for equivariant input-output mappings that is out there, because molecular graph networks are a bit different on their like input-output like objects. And so yeah, we decided to use this one. And so how does this thing work? Well, it is a graph neural network, so it has messages and updates like this M and F things. And they could look like this, or they do look like this in SCGNN. So these are these Clebsch coordinate tensor products where we have some features and some attributes that steer the features. And so this whole thing is one layer of SCGNN. So yes, these are the messages. This corresponds to this equation, and this is the update, which is updating one node. So on top of this thing, we started thinking of, so the problem here is if we have like a bunch of features, this is some latent space, and then with what do we steer them, right? So if we have many things on the right as well, then we would have too many parameters, because so the deep learning and machine learning part of this thing is, so there are some things on the left, there are some things on the right, there are ways to combine them. And so we learn scaling coefficients, so weighting coefficients like in the middle. Now, if we have many things on the left and many things on the right, we would have way too many coefficients, like all of a sudden. So that's why we try to have like as little things on the right as possible. And so the idea was, if we put these historic velocities and stuff in the features, like we encode them with the encoding layer, what do we put here? And so, well, steering with this historic data also makes some sense. And so the question was, how do we implement this, right? And so we investigated a few different ways, and that's this paper actually. These historic attribute embeddings, right? And attribute embeddings because these are the attributes used for steering. And so one way is just the arithmetic mean. So think of like 3 historic vectors and just the arithmetic mean something in between. Another way would be to have a weighted mean where we learn like 5 parameters per layer actually. And then the most complex version of this would be its own embedding tensor product, which is like one more tensor product, but a pretty small one, which is used only for the embedding. So yes, we did this, and what we got, yes, took us a few months. And so why did this happen? Well, because we had to build all the infrastructure to train these things, right? So those of you who have worked with equivariant GNNs know that they are kind of slow, like compared to non-equivariant ones, factor of 5 to 10. And so we started building our own like infrastructure in JAX. And so this is this thing here. Lagrange bench is our project that emerged through this whole thing. And so Lagrange bench is this Python library that offers all these utilities to run these problems in JAX, which is a bit faster than PyTorch and other libraries. So yes, we have this data and setup, which essentially like provides all the utilities around the data, and then we have the training utilities, which take care of all the training plus some training strategies from like recent papers, and then yeah, evaluation is like all these like kinetic energy, for example, measures, or we have the synchron distance, which is well another measure, and so on. And then we did implement a bunch of models. Well, SCGN is this equivariant one. This one is this kind of older one, non-equivariant one, and these are so we were experimenting. But so yeah, this thing is out if you are interested. Yes. And so yeah, please. Yeah, someone used the QR code. Thanks. Okay, so and so these are our results. Now, these are these measures that I was talking about. So there's the mean squared error on positions, right? So we care about the evolution of the particles, right? And we can just compute the squared Euclidean distance. And so these are the errors, and so we see that with all these, so SCGN average is this averaging embedding, then there's this linear weighting embedding, and then there's the tensor product embedding. And so we see that all of the equivariant ones are much better than about which data is this actually? Yeah, this is the Lagrangian. So this is the Lagrangian. This is the reverse pose offload. This thing with the channel. So, for example, we see that on this decaying problem, apparently equivariant networks are much better in terms of this loss, and well, eventually also in terms of the other losses. The synchron distance is an optimal transport measure of how different two particle distributions are. Meaning, so we have the evolution of the like testing data set, and then we have the evolution that we generate, and we can compare what is the optimal transport distance between like perfectly matching the particles. And so yes, this tells us something whether they are clusters. So if there is an empty region somewhere in the one thing and in the other it's populated, and it takes a lot of work to fill it, right? And so that's why we looked at this thing to quantify distributions. And that's so here again we see that this thing over the simulation length is larger for the non-equivariant ones, and eventually indeed the more complex the embeddings are, the better the loss. Like you can see this, for example, here, like this is the most complex thing we have. And so this is just a quantitative like table of the previous results, more or less. And so now I was talking about turbulence to give you the direction where this whole thing is going. But so at this level, this thing is not really useful in the practical sense, because so we're training on every 10th step of the numerical simulator, meaning numerical simulators are pretty fast because they're pretty simple. And so 10 steps of the numerical simulator take around 100 milliseconds. And now these GNNs, like not the non-equivariant one is faster, so this will be a speed up to some extent. But the equivariant ones are not really faster; they're actually slower. And so, but as I said, this is not the final goal. We're just developing methods that could eventually go like extrapolate to turbulent cases and so. Yeah. So the code is also on the internet. So this is the Lagrange branch code, and this is the particular stuff for this paper. If you're interested. And yeah, thank you, and I'm happy to answer your questions.
Let's thank Artur. Questions? Yeah. I guess that person was the first.
Thank you. Thinking about turbulence, so if your neural net should give you information on the very fine scales, right, you would have to train it on the very fine scale data which you have to obtain. So you would have to run lots of very resolved simulations. So in the end, you just, I mean, you have to do these simulations anyway then for the in order to obtain the data, right?
That's true. Yes. What's the question?
So you have to do many highly resolved simulations to get the training data if you want to do turbulence and code turbulence, right?
Yes, that's true. Actually, this is what I'm working towards right now. Yes, there was also this paper by the Google guys in the Google Brain or something in the US doing climate PDE stuff, and so they were also talking about generating their data sets was the most the most compute intense part of the project, right? So yeah, this will eventually happen here as well. Now the cool thing is graph neural networks have, well, they use local interactions, right? So as long as your data domain is large enough to have a decent receptive field, you can then run this learned dynamics simulator on like arbitrary large systems, right? So in this sense, we don't need extremely large sized data sets, but the data sets need to be eventually diverse enough, right? So yeah, generating the data is a problem. Yeah.
Okay, thank you. There is another one.
So you said you use symplectic Euler for the time stepping, but it was, maybe you mentioned it, but it was not fully clear to me whether there is some symplectic structure that you want to preserve.
Okay. To be honest, I think this slide is somewhat informative. Yeah, not really. Wait, where was it? Yes, so that's essentially what I mean by symplectic Euler. I mean, yes, okay. Symplectic Euler comes from molecular dynamics because, well, it's symplectic, and so there these things matter. To be honest, we use this because it was used in one of these previous works, and because it's probably the most intuitive thing to do if you want to be first order and don't care about integrator schemes. So yeah, there's no particular reason, just the simplest thing to do.
More questions?
Yeah, thanks for the nice talk. I was wondering your error evaluation at the end. The values were, I mean, pretty low compared to most machine learning that is done. Did you use single or double precision in your framework?
You're talking about this table?
Yeah.
Yes. Okay. Well, yeah, we didn't rescale the data, so these are really the numbers that come out of this thing. So yes, yes, the precision thing. We did use double precision in the data pre-processing, data loading. This is in double precision to not because to generate the inputs we compute velocities out of positions being, well, distances, and so. We wanted to have the highest quality of the data, and because this is not a very compute-intense part, this is a pre-processing on the CPU. So this was in double precision, and the model itself is in single precision. We actually did play around with that. We did train a model in double precision, but it didn't matter too much for the machine learning part, and so.
Okay.
Yeah.
Thanks.
Okay, I think we should move to the next speaker. Let's again thank Artur.